Hi, everybody. Today I'm going to be talking about Postgres table bloat. We're going to get started in a second, but the overall idea of this talk is discussing the transition from doing Postgres at a smaller scale to Postgres at scale and what that actually means for you and the problems it can lead to with your database access patterns and configurations like autovacuum, and also how to prevent things from going wrong in the first place. So without further ado, let's get started. So as I said before, my name is Chelsea Dole, and today I'm going to be talking about managing your tuple graveyard. And what exactly a tuple graveyard is, we can get to in a couple slides. I work at Brex, which is a fintech company originally known as the credit card for startups, and now working in fields such as expense management software. Previously, I was a data engineer and backend engineer, and currently I'm the tech lead of the data storage team. On the data storage team, we manage Postgres at scale at Brex, hundreds of databases, managing their infrastructure, helping teams with query optimization, and more. Today, we're going to be starting off our discussion with learning about MVCC, or Multi-Version Concurrency Control. Then we're going to be using that as a platform to understand table bloat, which is the focus of the talk. We're going to get into what exactly it is, what causes it, and how to mitigate it. And then later, we're going to be talking about extensions such as pgrepack and pgstat-tuple, and also autovacuum configurations. Finally, we're going to round out the talk by taking a bit of a higher level, holistic view, talking about how to design bloat-aware database access patterns and architecture so that you don't have to run into these problems in the first place. So without further ado, MVCC, or Multi-Version Concurrency Control. MVCC is basically just a set of rules that Postgres abides by. And the point of it abiding by these rules is to achieve two seemingly contradictory goals. First of all, transaction isolation, and second of all, fast performance. But what exactly do these things mean, and why are they contradictory? Transaction isolation is the I in ACID. If you're familiar with that acronym, it stands for atomic, consistent, isolated, and durable. So that's the transaction isolation is the I. This is what in computer science they refer to as the underlying functionality or definition of a database transaction. Overall, for us, this means that data within the transaction should represent table state when it starts, even if things change over the course of a longer transaction. And completely on the other side, fast performance. This is kind of self-explanatory. We want it to go fast for reads and writes. And what this typically means at a slightly nitty-gritty level is that writes don't block reads and reads don't block writes, therefore enabling fast performance. These goals are contradictory at face value, at least, because in order to have transaction isolation, we need to use database locks. However, if you use them a simplistic way, then you're going to have cascading locks, which kind of stomp on each other and lead to bad performance. If you think of a basic locking example where there's a single write lock and a single read lock, where transactions wait in a queue to sort of take that write lock, do something, pass it back to the next transaction, you can see what I mean. If we were to implement this in Postgres, it would not work with the way that databases are used today, which is dozens, hundreds of connections at once, potentially. MVCC takes an approach that focuses on the MV of the MVCC, the multi-version part. Basically, it implements row versioning via tuples. A tuple is the internal representation of a row version that's stored on disk. I think of a row as a more logical construct. It's the logical idea of a row. But what actually comprises the row stored on a database's disk is one-to-n tuples under the hood. Those tuples represent how the data has changed over time. We have two types of tuples we talk about, live tuples and dead tuples. A live tuple is the newest version of that row's data, or any older version that's still being used by something. So for example, if you have a 30-minute query, the data may have changed in that time, but the older version is still necessary because that 30-minute query still sees it as a live tuple that's being useful. Whereas a dead tuple is basically everything not covered in that definition. It's an old row version that's not being used by any running processes. So all DML operations, such as insert, update, delete, are actually, under the hood, achieved only by inserting new tuples and updating metadata. But what does this actually mean? First of all, in order to in order to get by this process, MVCC uses transaction snapshots. A snapshot, in this case at least, because snapshot is sort of a ubiquitous word used in several different places in Postgres, is an internal in-memory data structure that Postgres creates on a per transaction basis. So every transaction has a little in-memory snapshot. It uses pieces of data such as xmin, xmax, and xip list to determine what tuples that transaction can see. Mostly it's using the first two, xmin and xmax. The xmin is the transaction ID, which inserted the tuple. The xmax is the transaction ID, which deleted it or updated it if that's happened at all. Null if it's live and has never been updated or deleted. XIP list is a bit of an oddity, and we'll talk more about it in a couple slides. But basically, this is a list of the transaction IDs of currently running transactions. Because of concurrency, even though generally xmin and xmax are monotonically increasing over time, that's not always 100% the case when you have transactions that may be very long running, but not finish at the end. Not finish for longer than something that can be completed within the full length of time. This is important because transaction ID is actually assigned at transaction start. So if you assign a transaction and then it takes 30 minutes to finish, then you might have many transactions which are completed and committed in that time it took. We're going to go through an example because it's a lot easier when you see it visualized. To use this example, we're going to use this example table here, where we have an ID column. We have first name, city, and updated at. We're going to be tracking employees or users and where they live. And we're going to internally to Postgres track xmin and xmax. If you were to query this as a user, you wouldn't actually see xmin and xmax, but Postgres is tracking them to use for its transaction snapshots. We're on transaction ID 600, and we're going to insert this new tuple. We're going to insert a new employee whose name is John. It's 2002, let's just say. So we're inserting this with the xmin of 600 because that's our current transaction ID, and we're inserting. Next, we're going to actually update John. John's going to move from New York to Seattle in 2023. So we're inserting a new, first we're deleting the existing tuple, and then we're inserting a new one. We do the soft delete by updating the metadata. So we add our current transaction ID of 605 to xmax for John's tuple in New York. And in the same transaction, we're inserting a new tuple with null xmax, meaning it's the most recent version, and he's going to now be living in Seattle. Now we're going to delete this new row with John in it. Maybe he's moving out of the company or something else. All we do to do this delete, just like an update, is we update the existing tuple with xmax of the current transaction ID of 609. So if you're thinking about this, you might think, okay, well, deletes are updates, which insert, inserts are inserts, which insert, deletes just add metadata. So are we just infinitely increasing our row count forever? Luckily, the answer is no. To get around this, we use vacuum. Vacuum has a lot of jobs, but the one we're most interested in today is the first. It deletes dead tuples from Postgres pages, which frees up the space for reuse. It also does things such as updating Postgres' internal stats via analyze, which improves the query planner's effectiveness. It updates the visibility map, which helps vacuum and index-only scan performance in the future. And also it frees up transaction IDs for reuse because they're of limited number, and this prevents transaction ID freezing, which in turn prevents transaction ID wraparound. If we were to throw back another example in vacuum, we would see this. Now we're on transaction ID 609, and you can see those two areas that we allotted for tuples are still there, but they're empty. They're now reallocable for new tuples, which may be inserted. One final example, I told you we were going to get back to XIP list, is an insert and a select at a similar time. If first we insert something, let's say we're inserting this new value into a table, Olivia living in New York. However, this insertion is going to take a very long time. It's a 30-minute insertion for whatever reason. And then after this transaction ID is assigned, a later select is going from select star. This select star's transaction snapshot is going to have an xmin of 611, but because this transaction ID for Olivia is still running, it goes in XIP list, which is sort of like a list that tells Postgres to address those XIDs on a case-per-case basis to see if they've been committed or not. A quick aside here about Postgres disk usage. I've been really careful in the wording that I use to say that vacuum frees up space for reuse. It doesn't reduce disk space. A page on Postgres is the smallest unit of disk space, 8 kilobytes by default, which stores bunches of tuples along with other metadata. Without explicit intervention, Postgres disk usage will only increase. Pages are created, but not deleted. So vacuum will delete the tuples within pages, but not the pages themselves. There are some exceptions here, which I won't get into, but are very rare. Now on for part 2, which is table bloat itself. We've finally been able to get to that. Table bloat is less than optimal page density. I'm taking this definition from PG Analyze, which I think had a very good talk on this subject. Overall, this means the number of live tuples in a page versus how many could hypothetically fit is not optimal. To visualize it, it might look like this. Something with high tuple density, lower bloat, would be like the top, where you have 3 pages storing 10 total tuples, versus the same 10 tuples in over double the number of pages below. Bloat is often problematic because with dead tuples occupying what would be space that Postgres could use for new tuples, it's forced to continue creating new pages. So even after vacuum runs and dead tuples are deleted, live tuples are now stored sparsely, using more I/O during scans. Going back to our example here, if you were to run select star on the first one, it would need to scan over 3 pages to receive the result, versus the bottom one would need to scan over 7 pages. So you're using more I/O to get the same result, even when it's been vacuumed. But I said often problematic. And this is because things are problematic when they actually cause problems, not just by default. Bloat is more like the underlying root cause of other problems than necessarily a problem in itself. Problems caused by bloat could be bad read latency because of that increased I/O, high or expensive disk usage if you're trying to save money, and also high or expensive IOPS, because if you're on something like Aurora or other managed services, you might be charged by IOPS instead of a more traditional billing method. Bloat basically occurs due to 2 things in tandem with each other. First of all, having update and delete heavy workloads. So bloat is caused by these pages being saturated with dead tuples. For example, user activity could cascade and cascade into lots of updates and deletes, or scheduled batch jobs might edit massive amounts of data at once. And secondarily, along with this first one, is badly tuned autovacuum configuration. Overly conservative or older default on older versions of Postgres, autovac configurations paired with this pattern is what leads to bloat. An example case study, which I've seen at multiple organizations, might look like this. You might have a machine learning feature store, which is storing hundreds or thousands of features per user with a uniqueness constraint around feature name and user ID, because, for example, user 61466 only wants one value for last login. We're going to have all right as upserts. So if it doesn't exist, I'm going to insert it. If it does, I'm going to update the value. And maybe our table size is around 300 gigs. We might have burst-based high volume write activity triggered by user activity. And maybe we're even super helpful and we decide, when machine learning engineers want to deprecate features, maybe they don't want owns house anymore, they don't need it for their models, then we'll have some sort of batch delete job. And finally, to kind of finish it off, default autovacuum configurations. The potentially dangerous areas of this are the ones that are in orange here, where all writes are upserts, high volume write traffic, and feature deprecation, which is basically just batch deletes, as well as autovac defaults. The rest of it, and even anything in this, is not necessarily bad. 300 gigabytes isn't that big, all things considered. When you consider when you consider it big data, it's more big data with a little b. But adding on all these database access patterns is what makes this concerning. Let's get on to how to quantify, mitigate, and avoid this, now that we've been able to understand what bloat is at a bit of a high level. Quantifying table bloat can be done in basically 2 ways. The first one is using an extension, or rather a Postgres contrib module created specifically for this purpose, or another one similar. Using pgstat tuple will return the precise value of your bloat. It will return how many pages are being used for active or live tuples versus dead, turn it into a percentage, and return other stats related. However, it can be very slow running and use lots of resources because it has to do a sequential scan over every page, and it can't use indexes because it's actually looking at the pages. So we'll have O(n) runtime based on table size. On completely other perspective, you have estimation queries. There's a lot of these online, and basically it's just open source queries that are using internally managed Postgres fields such as PG class rel tuples to get estimates of those same numbers. You want to run analyze first, which should refresh those stats based on a sample of table data, but this will always run an O(1) runtime, just with less accuracy. If you were to take the first approach using PG stat tuple, you would run it like this. And your return value would look something like this. You would see your table length in bytes, your total number of live tuples, the percentage of total tuples which are live, and then the percentage of total tuples which are dead. The percentage we're mostly going to focus on is this dead tuple percent, which in this case is 2.46. Versus if you were to use the other method of an estimation query, and I've linked an example popular estimation query at the bottom of the slide, it would look something like this. You'd run analyze, and then you'd run a very long query, which, because you're a good DBA, you definitely read over in completion just to make sure it's not doing anything too crazy to your database. And it'll return to you this, your estimated table length in bytes, your estimated bloat also in bytes, and then the percentage of real size, the first row, used by bloat. In this case, your bloat percentage is 9.46. If you've been paying attention, you might notice that these two methods aren't very comparable. Neither one is necessarily terrible or great. However, the first one, using pgstat tuple, is using a percentage of dead tuple count, versus the latter estimation is using the percentage of dead disk space. So tuple size varies wildly, and page-level opportunistic pruning can leave 4-byte tombstones, even after it's been soft deleted, which means that it might not be very accurate to look at the dead disk space estimation compared to dead tuple count. If you want more info on this, because I'm not going to go into depth in this talk, I'd recommend watching Bloat in Postgres, a Taxonomy, which is a presentation given by Peter Gagan most recently at Scale 2023. So now that we figured this out, we have our numbers, percentage of bloat, we can ask how much is too much? And annoyingly, the question, as always, is answered by it really, 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 really depends. However, I'm going to give some of my personal rules of thumb, which have applied to production systems I've worked in. When you're dealing with very small databases, or very small tables rather, because these all refer to tables, up to 70% of bloat is fine. This is high and not ideal, but it's not going to impact anything. And remember, bloat is only bad if it has downstream negative effects, like anything else. To small, medium tables, 1 to 30 gigs roughly, up to 25% is acceptable. 30 to 100 gigs, I would say up to 20% is acceptable. And very large tables, which is over 100 gigs, up to around 18% is acceptable. These are all based on my personal experience, and they're up to change depending on what sort of system you work in. When dealing with bloated tables, configuring autovacuum to be more aggressive, and then repacking and rebuilding are two approaches you can take to dealing with tables that are already bloated. First, you can configure autovacuum more aggressively. The first thing you'll want to tune is autovacuum vacuum scale factor. By default, it is 0.2, which means 20% of table size. And this basically means that at least 20% of the table must have changed since last vacuum in order for vacuum to be triggered. This means that making it smaller means it'll trigger more frequently. If you were to change this to, say, 0.01, this would mean that only 1% of the table would need to be updated or deleted in order for it to trigger. Secondarily, you can use this in tandem with autovacuum vacuum threshold. Postgres internally will use these two to play off each other in order to figure out when autovacuum should be triggered. Generally, you want to keep this as default. Its default is 50, and just trigger the first one, scale factor. But there is a nice trick that people often use where you can set scale factor to 0 and then change threshold to a solid number. What this will result in is it not being triggered by a ratio of your total tuples change, but instead being triggered on just a number of tuples that have changed since your last vacuum. So in this example, you would have changed a couple 100,000 tuples before it triggers, no matter your total table size. Secondarily, you can tune autovacuum vacuum cost delay, which is defaulted to 2 milliseconds in PG11 and later, but over at 20 milliseconds before then. And it doesn't matter what Postgres version you're on. If you're using, relatively modern hardware, you should just tune this up to 2 milliseconds. Secondarily, autovacuum max workers. This is worth tuning if you have probably multiple thousands of tables on one database server. And in order to check it, I recommend looking at pgstat progress vacuum to see how many vacuums are currently running at one given time. If you're always maxing out at the default of 3, then you may want to consider tuning upwards one by one and seeing the impact it has on your system. Secondly, you can rebuild or repack existing tables. The first in-the-box way to do this is with vacuum full. This will rewrite the table and all of its indexes onto a new disk file with no extra space. However, in exchange for this, it will take an access exclusive lock, which blocks all reads and writes to your table. Not exactly ideal for almost anybody. The wasted space is returned, but overall this is not recommended due to this very heavy lock. Instead, you can use PG repack or PG squeeze. This will duplicate the table, copy over the incoming data via triggers, and alter the table names to switch them under the hood, taking an access share lock. This requires 2x the current table disk in space and a good amount of CPU and RAM, and in my opinion can be sometimes quite flaky, but I would still recommend it because even in the worst failure scenario, if you just cancel the PID of the process, no data is lost. In the worst case scenario, if it fails mid-repack, you have to go manually drop and clean up the temp tables, but you're still in a good state. Comparing PG repack to alternatives such as PG squeeze is also valuable. I've only used repack for full disclosure. This is an extension you can install and you call it externally from a client. This means that there's no change to the binary, so it's supported by things like RDS. Whereas PG squeeze is actually a change to the binary, so it has additional features. You could say it's more feature complete, allows you to schedule rewrites, etc., but you're not able to use it on RDS or managed services, and I would say it's more invasive to the system overall. Finally, let's look at designing bloat-aware data access patterns, because the goal, again, is to make it so that we don't have to run repack or these steps beyond minimally or occasionally. I'd recommend when you start working with a database to think about how, when, and for what purpose are you going to be reading and writing to it? What percentage of transactions do you expect to be reads versus inserts, updates, and deletes? This could be very informative to understanding how likely you are to run into bloat and other issues. Finally, or secondarily, roughly what percentage of data growth do you expect to occur annually? Where do you expect to be in a year if the current system maintains? And finally, what sort of access will or won't you support? As a data team, do you allow people to have certain access patterns? Or will you ensure that they're only allowed to access the data in certain ways? Now I'm going to go over some rules of thumb. If your app is update and delete heavy, question whether you can redesign your data access patterns to have few updates and deletes. For example, if user actions trigger a burst of updates, can you update each row once instead of n times? Or if you're updating the same row many times, maybe you want to consider an append-only log-style table and then send read queries to look at the most recent row. Upserts originating from a queue can also be partitioned, so at the very least, they're always processed by the same worker and not having conflicting locks. If you have regular large delete jobs, you might want to see if your workload is compatible with partitioning. You can also make sure you always use a reasonable batch size in your deletes rather than one large transaction. And instead of having one large delete job, you can consider reducing the size and configuring autovacuum. So maybe it'll trigger on a smaller, more frequent basis instead of one large, potentially interrupting vacuum. Finally, always a good question, are you reinventing any wheels? My rule of thumb is that using Postgres for things outside of Postgres' intended wheelhouse is fine, often using great extensions available in open source, up to a certain scale. For example, if you're doing full text search, using 25 gigs of data on Postgres is going to be great. If you're using 100 gigs, you may want to consider something like Elasticsearch. Or if you're doing a key value store, if you have a 50 gig key value table with 80% of the traffic being reads, that's fine on Postgres. But if you have a larger table where most of the traffic is writes or upserts, like we talked about, that might be a case where you want to use Redis instead. And as always, you'll notice the little star in the bottom right is back, so it does depend on your application. That's the end of my talk. Thank you so much for staying with me through this process. I really hope you learned something about bloat, and I hope that you have great access patterns for the rest of your life. Thank you very much.